We built the modern world out of concrete. It's cheap, it's strong, and it's everywhere. But there is one fatal flaw: it cracks. And once water and salt get inside, it dies from the inside out. But what if concrete could defend itself? Instead of always relying on repair crews to close highways for months, imagine concrete simply healing on its own. This possibility leads us to a new development: self-healing concrete. It's how bacteria, fibers, chemistry, and some seriously smart engineering are trying to save our trillion-dollar infrastructure. We'll look at some case studies, compare costs over 50 years, and ask the hard question: if it's so good, why isn't it everywhere yet?
The one that we're actually working on is to use some sort of bacteria that they could produce stones, right? Sometimes I call it stone-making bacteria.
Our goal is mainly to increase the durability and to reduce maintenance and increase service life. That if service life is longer, it's more environmentally sustainable because you will have less waste material and so on.
To see why self-healing is important, let's start with the problem. Because to understand the cure, you have to understand the disease. Concrete is highly effective at resisting compression, which means it can withstand heavy weight pressing down on it. You can stack a mountain on top of it, but try to pull it apart, a force called tension, and it breaks. That's why steel rebar or reinforcing bars get added to provide strength against pulling forces. But here is the killer: every tiny crack, even the ones you can't see with the naked eye, let in the elements. Chlorides from road salt, CO2 from the air, water, acids from rain. When that water hits the steel rebar, a chemical reaction starts. The steel begins to oxidize, rust. And here is the brutal part: rust takes up 6 to 10 times more volume than the existing steel. It expands like a balloon inside a rock. And that expansion exerts enormous pressure, thousands of pounds per square inch, blowing the concrete apart from the inside. Engineers call this concrete cancer. And once it starts, you can't stop it. You can only cut out the damaged section and replace it. That means jackhammers, traffic jams, and millions of dollars. This isn't just a nuisance, it's dangerous. America's infrastructure earns a C- from the American Society of Civil Engineers. One of every 3 bridges here is over 50 years old. In Europe, thousands have outlived their original design life. Their repair bill globally? The World Economic Forum estimates $97 trillion by 2040, just to keep infrastructure at a safe level. That is more than the combined GDP of every country on Earth. Faced with this challenge, we have 2 choices: tear it all down and rebuild, which costs a fortune and has a huge carbon footprint, or develop concrete that heals itself from within. Before we explore the new opportunities, let's look at how concrete already tries to heal itself. Here's something most engineers keep quiet about. Regular concrete already has some self-healing built in.
Concrete does have some self-healing properties even without making any changes, because there are always some unhydrated cement grains, binder particles in the matrix, and so if a crack appears, these unhydrated binders can be exposed to water and start producing reaction products that can heal small cracks. But yeah, this potential is limited, and the older the concrete gets, the less self-healing potential, autogenous self-healing potential you still have available.
Inside every slab of concrete are leftover, unreacted cement grains called binders. When you mix concrete, not all the cement reacts. Some grains remain inactive. If a crack is smaller than 0.1 millimeters, thinner than a human hair, and water gets in, those grains wake up. They hydrate, meaning they react chemically with water. They expand and form calcium silicate hydrate, CSH, which is the same glue that holds concrete together. Over weeks, they can seal the gap and stop the leak. But here's the catch: that only works for microscopic cracks. The moment that crack hits 0.3 millimeters, about the thickness of a business card, game over. The water flows freely, the steel rusts, and passive healing fails completely. To repair substantial cracks, the ones that threaten bridges or tunnels, we need active healing. That's where the solutions become biological, chemical, and highly innovative. To explore the most promising fix, consider this. What if I told you that the answer to crumbling roads lives inside a volcano, or at the bottom of a salt lake, or inside a 500-year-old bottle of beer found in a shipwreck?
This bacteria, they could survive for a long time, and they could go to a dormant stage, and when you need them, they could wake up and they could start like healing the crack.
Scientists have found extremophile bacteria, meaning bacteria that can survive in environments with extreme conditions, mostly from the Bacillus family. These bacteria naturally produce calcite, a form of limestone, which is the same materials that pyramids are made of. These bacteria eat calcium lactate, a nutrient, and through a metabolic process produce calcium carbonate. In plain English, they pee out rock. Here's how it works. You mix the bacterial spores into the wet concrete. They sit there dormant for years, maybe decades. They don't need food, they don't need oxygen, they just wait. Then a crack forms. Air and water rush in.
When a crack appears, they get in contact with nutrients, with water, and they start germinating, and they produce calcium carbonate, kind of limestone that fills the cracks.
That limestone is chemically identical to the concrete itself. It bonds perfectly, it's waterproof, and it can seal cracks up to 1 millimeter wide, 10 times bigger than passive healing. And here's the kicker. The bacteria can repeat this process. Every time a new crack forms, they wake up again. You get a permanent, waterproof, autonomous repair system that works 24/7 for the entire life of the structure. No workers, no traffic jams, no jackhammers at 2 a.m. Bacteria are the champions of self-healing right now. But before we get into the details, let's look at 2 other methods quickly, because each has its own strengths. Method 1, microcapsules. You encapsulate a liquid healing agent, like polyurethane, epoxy, or mineral compounds, inside fragile polymer shells, which are essentially tiny breakable containers. You mix those shells into the concrete. When a crack forms, it ruptures the shells, releasing the glue. The glue, such as polyurethane, a type of plastic, flows into the crack and hardens when it comes into contact with air or moisture, sealing it. Simple, effective, proven in labs. The downside? It's a one-shot deal. Once the glue is used, it's gone. If the same spot cracks again later, conceivably from thermal expansion or a new load, there's no second healing cycle. And the capsules are expensive to manufacture. And then there is the second method, vascular networks. Inspired by human skin and tree sap, you embed hollow channels, glass tubes, polymer pipes, or 3D printed networks inside the concrete. These channels carry a healing agent. When a crack intersects a channel, the tube breaks and the agent flows out. If you connect the network to an external reservoir, you can heal the same crack multiple times. This is the most powerful method for critical structures like nuclear waste containers or deep-sea oil platforms. But it's complex to cast. The channels can slightly weaken the concrete, and if the network gets clogged, you're done. So, which one wins? For most everyday infrastructure, bridges, tunnels, seawalls, parking garages, bacteria are the frontrunner. Why? They don't need an external pump. They don't need fragile capsules. And they keep healing again and again for decades. Let's talk costs. If this technology is so brilliant, why are we still driving over potholes? The answer is upfront costs. Regular ready-mix concrete costs roughly $120 to $150 per cubic meter. Bacterial self-healing concrete? Depending on the spore concentration and nutrient distribution system, it can cost 20 to 50% more, up to $225 per cubic meter.
Of course, it's going to be expensive, but in a long term, in a service life of a structure, right? How much we're talking about? Like if it's going to double the service life, right? So maybe like the increase, 20-30% increase in the cost divided by 2, it's not going to be that much, right? Or like it's going to be like even like cheaper in long term, right?
Dr. Farnham makes the bridge painter argument. A bridge doesn't just cost what you pay to build it. It costs what you pay to keep it standing for 50 years. Imperfections, traffic delays, epoxy injections, concrete patching, shutting down lanes for a month, replacing entire segments. A 2018 study from Delft University looked at a typical highway bridge. Over 50 years, conventional concrete costs $8.2 million in maintenance and repairs. Self-healing concrete, $3.1 million. The upfront premium was recovered in just 12 years. After that, it was pure savings. But here is the cold truth. Governments and developers think in election cycles and quarterly reports. A politician wants a ribbon-cutting photo today. A developer wants to sell condos next year. They pay the lower price today and leave the collapse, the lawsuits, and the higher taxes for the next generation. It's not an engineering problem, it's a human psychology problem. There is one more big technical difficulty. Bacteria are tough, but they aren't invincible. If you just dump them loose into the concrete mixer, the spinning blades, which are designed to pulverize rocks, kills most of them. That's a lot of dead bacteria, and dead bacteria don't heal cracks.
You could lose 80-90% of the bacteria during the mechanical mixing, but what if you protect them in this fiber? So that's what we're doing, right?
This is genuinely clever. Dr. Farnham's team impregnates bacterial spores into recycled plastic fibers, the same type already used to control cracking in high-performance concrete. The fibers act like armoured personnel carriers. The bacteria survive the mixer, are evenly distributed throughout the concrete, and when the concrete cracks, the fibre bridges the crack, holding it together mechanically. And right there, at the perfect location, the bacteria wake up and start producing limestone. It's a two-in-one solution: structural reinforcement and biological healing. This solves the dead bacteria problem. And because the fibres protect the bacteria, you can use fewer spores, thereby lowering costs. Some lab tests show that fibre-protected bacteria achieve 95% healing efficiency, compared to just 20% for unprotected spores. This is the kind of innovation that turns a lab curiosity into a real-world product. This isn't science fiction. It's already working in the field. Right now, in structures you could visit tomorrow.
Tunnels generally should be watertight. Well, you wouldn't like to drive through a leaking tunnel, I assume. The thing is that because these are quite massive elements, they are more prone even to early age cracking. So they might show cracks already in the first week of their life. And then they have already to be repaired before they can even start to function. So that's maybe one situation where self-healing is very attractive. Especially we have done some trials with these super absorbent polymers, where we have shown that in these massive walls, a lot of the cracks can be avoided.
The A73 tunnel in the Netherlands used bacterial self-healing concrete in its expansion joints. These joints are notorious for leaking. After 3 weeks of water exposure, cracks that would normally leak 5 litres per day healed themselves. No maintenance crew, no traffic closure, no chemical sealants. In the UK, researchers embedded microcapsules in a pedestrian bridge. After 2 years of weather exposure, the bridge had healed 90% of its active cracks. The structure was actually healthier than the day it was built because the healed zones were denser than the original concrete. Parking garages are actually the perfect first market. They crack from thermal expansion and vehicle loads. They leak onto cars below, and the repairs are a nightmare because you can't close the garage for a month. Self-healing concrete could eliminate 80% of parking garage maintenance. So why isn't every new parking garage using it? The only reason we don't see this everywhere is not science, it's paperwork. Building codes don't yet include a checkbox for bacterial healing. Standards organizations like ASTM and ISO are still writing the test methods. How do you measure healing capacity on a construction site? How do inspectors verify that the bacteria are still alive after 5 years? Right now, there's no standardized pass-fail test for self-healing concrete. So contractors are scared. If they specify it and something goes wrong, who's liable? The concrete supplier? The bacteria manufacturer? The engineer? And there's a perception problem. The word bacteria scares people. They think of infections or rot. They don't think of limestone-producing harmless bacillus spores that have been used in probiotics for decades. But change is coming. The European Union's Resilience project spent €8 million proving self-healing concrete on real bridges. China is building demonstration roads, and the first ASTM standard for self-healing concrete is expected sometime this year, 2026. The technology is ready, the economics work, now we just need the rules to catch up. So, is self-healing concrete the answer? Will it save our bridges and tunnels? It won't stop a bullet, it won't hold up a skyscraper by itself, but for the things that matter most, bridges, tunnels, seawalls, parking garages, water treatment plants, it changes the math entirely.
Our goal is mainly to increase the durability and to reduce maintenance and increase service life. So this means we will also normally have less interruptions of traffic for repairs and so on, that if service life is longer, it's more environmentally sustainable because you will have less waste material and so on. So also, reduction of all the social effects that go along with repair of bridges and roads and traffic interruptions. That's the point.
Every ton of cement we produce emits nearly a ton of CO2. Concrete is responsible for 8% of global carbon emissions, more than the entire aviation industry. If we can make structures last twice as long, we cut the industry's carbon footprint in half. That is not only an engineering win, that is a planetary win. The bacteria are ready, the fibres are ready, the economics work. The only thing missing is the will to pay a little more today to save a lot more tomorrow.
With the idea of self-repairing and self-healing and self-sealing, the major impact would be on the durability performance and how it could prolong the durability of a concrete structure, because normally the durability issue comes with aggressive chemicals and the environmental conditions, right, rather than the structural deficiency, right? Because the crane codes, they assume it's going to crack, and when it cracks, there are going to be like pathways for any sort of like aggressive chemicals to get in, and those fluids or like chemicals are going to create durability issues, right? By repairing and sealing, you actually eliminate permeation of this aggressive chemicals. That's going to be I think, the better impact that you're going to get from this type of technology.
Conceive a world where roads never get potholes, where bridges don't need inspection every 2 years, where a parking garage lasts 100 years without a single repair crew. That world is closer than you think. And it's being built one crack at a time by bacteria that sleep for decades, wakes up on command, and builds stone.